Right, hi guys, welcome to my lessons. I think you are the last in the queue for getting a lesson from me. I hope it will make sense, and I hope that you keep it and listen to it again and again, so that you've basically got one of my lessons on video, and you're going to get more of them. So yeah, I hope you've printed out the notes. I have loaded them on Google Classroom. And yeah, so what we're doing now is that we are heading towards intermolecular forces. All right, but before we get there, we have to do a few other things. So this is under chemical bonding, molecular shapes, and intermolecular forces. So we're going to do the first two. I'm going to just remind you about your chemical bonds, because that is relevant to the section, and just I'm going to blow your mind again. I don't know if I'm going to blow your mind or disappoint you, but here goes. All right, so remember we got our three different chemical bonds. So the first one is your metallic bonding, and there's a sea of delocalized electrons. Okay, now metallic bonding is called metallic bonding because it actually does happen between metals, atoms that are metallic. All right, so we got our sea of delocalized electrons. Remember, what does delocalized means? They are free to move, okay? And the part of the atom that is now left behind after an electron has lost it, that whole part, including the electrons that are left, has now got an overall charge of positive. So that is what the positive kernel is called. So when you have a look at your definition of metallic bonding, you'll see it says there a sea of delocalized electrons around positive kernels. That's because it's the center. So for example, if you have your nucleus, you know your nucleus is positive. Then you have your two electrons here, and let's say you had an electron out there as well. So this would be lithium. So what happens is if that electron is lost, the rest of that's there becomes positively charged, because the number of protons outnumber the number of electrons, and overall it's positive. So this will then be called the positive kernel. So we don't call it the nucleus because there's still electrons around there in an energy level. Okay, so yeah, example, copper wire, iron rod, and so on. So other info, the metallic bonding is the thing that gives metals all their properties like conduction, malleability, and ductility, okay, or being ductile. Okay, so then we get to covalent and ionic. But before I do this, I want to just say, up until now, I've allowed you to learn covalent bonding as occurring only between non-metals, or between non-metals only. And ionic bonding is between a metal and a non-metal. Well, this is where you're going to be disappointed or minds blown. We are actually now going to start looking at the electronegativity of each atom as they are bonded. So if you have if you take the electronegativities and you find the difference, so you subtract the one electronegativity from the other, you take the bigger one minus the smaller one, okay? If you land up with 0, well, that's obvious that the electronegativities are the same, and when you subtract the same from the same, you get 0. And this then results in a non-polar covalent bond. They are both pulling bonded electrons equally. Okay, so we're talking about the bonded electrons. If your difference in electronegativity, so higher minus the lower, is between greater than 0 and smaller than or equal to 1.7, we then say it is polar covalent. One of the atoms is pulling the bonded electrons more than the other. If your difference in electronegativity is greater than 1.7, it is then ionic. So girls, it doesn't matter if it's metals or non-metals. This is now what overrides that. Okay, so remember, covalent is a sharing of bonds, the sharing of electrons. Ionic bonding is the giving and receiving of electrons. Okay, so just to get you onto the same page here, that this is what's happening with your electronegativities now, and you can no longer just guess the type of bond, but you can actually work it out what type of bond you've got. Okay, so Lewis diagrams for molecules with single bonds. Now I know this is tedious and you don't like Lewis structures, but you have to do this so that you can start getting the shapes right. Okay, and when you get the shapes right, that means that you can start getting your intermolecular forces right. Okay, so I'm just going to show you just these where there are draw the Lewis structures for the molecules. These are single bonds. So in other words, each atom is bonded to another atom with one bond. Okay, so let's do this. So if I go F and F, okay, I'm going to make one, one open dots. So we know that fluorine is in group 7 or 17, and we are going to do it like that. And if I color those, sorry, I've made them so far away from each other. And we know that that is happening there. Now, girls, these are our bonding pairs over here. Okay, this should be a bit closer. I'll draw the others closer. But this is only going to equate in one bond. Don't forget to draw those other electrons. If you draw it without those electrons, your Lewis structure is wrong. Okay. So I'm going to teach you something new now. It's called the Cooper notation, and you've actually been seeing Cooper notation for a long time now, and you've been using it. So what Cooper notation is that it drops all the dots, and instead of showing the bonding pair, not like this, but closer together, I'll show you in the next one, it will be a line to show the bond, and that is Cooper notation. So every bonded electron is represented by a line, bonded pair of electron. So there it is there. So NH3. So if we go N, we've got our lone pairs over here. Okay, there is our Lewis structure for nitrogen. I'm sorry, it's and then we've got our hydrogens. Okay, now each hydrogen is sharing one electron with nitrogen. So in other words, they are each of them singly bond. We can't say this is a triple bond because there's 3 hydrogen atoms bonded at 3 different places, and each of them have their own single bond. Okay, so there are 3 single bonds here, not a triple bond. So your Cooper notation would look like this. You can include, in fact, it's encouraged to include your lone pair of electrons. And you can then, your bonding pair, so the the electrons that are sharing, they will be represented by a line now. Okay, actually, I want you to draw those lone pairs. Okay, then we've got HF. So again, F, if we have a look like that, it's in group 17, so we know that there are 7 electrons around it. And we have H, and now you can see why it's important to draw all of those electrons, because here H only has that 1 electron, so it only has 1 bonding pair that it's sharing with F, but it doesn't have any of the other electrons, and that's why it's important to draw your halogens like that. So this lands up being like that in Cooper notation. H2O, I don't know how many times we've done H2O. And we've got 2 lone pairs in H2O. We have got 2 pairs of bonded pairs, and they are over there. Okay, so if we take a look, we've got our lone pairs. We then can draw it like that with the Cooper notation. Okay, so this actually has a name where you can draw the Cooper notation, and the Cooper notation is very useful for finding the shapes, and you can already see the shape. You can see the bent over here, but it comes from doing the Lewis structure first. So if you know your Lewis structure as well, you can then do that. I wonder, I'm just going to make a note, just show you. I'm going to change the color of the hydrogen one here and here, just so that you can see that there was a difference between them. Okay, sorry, the fluorine should have been drawn closer, so yeah. Okay, next page. So page 2, Lewis diagrams. Now this is showing the formation of molecules that contain a double or triple bond. Okay, so our Lewis structure. So carbon dioxide. Now, I know we looked, you've already seen that there's a central atom with atoms around it. It's very difficult to determine which is the central atom actually, because remember in chemistry there's a suggested general rule of thumb, but it's not a hard fast rule. So in this case the rule works in that the atom with the lowest electronegativity is the central atom. So carbon has a lower electronegativity than oxygen. So carbon becomes the center. Okay, now I'm going to just show you briefly on my piece of paper here what's going to happen. So carbon, we know, has Lewis structure that looks like that. It's got 4 dots around it. But what happens now is when it is bonding with nitrogen, remember nitrogen looks like this. Okay, it's only got space for 3. So here it's got space for 3. This one has space for 4. Okay, so our hydrogen here has its one space over here. Okay, so what's going to happen is that the nitrogen, 3 of the nitrogen electrons are going to share with 3 of the carbon electrons, leaving 1 electron to share with hydrogen. And so what happens is that this doesn't really happen in real life, but we are going to move our electrons around so that we can see those 3 bonds. Just for this notation, okay? So, and for Lewis structures. So what happens is my carbon's electrons move around there, okay? My nitrogens, actually I'm going to do crosses, remember we've done crosses before, move over there, and there are my lone pairs of electrons over there. So those are there. Basically what you want to see is you want to see that if you drew a line from the one electron to the other, you're actually going to get your Cooper notation. So there, and this is now hydrogen. So when I draw Cooper notation, I have carbon, 1, 2, 3 bonds, and this is now called a triple bond. My lone pairs are on the other side because remember your electrons repel. So these are repelling against each other, but they also repel those lone pairs. So they go as far away as possible. And we then do this. This is still not looking at the shapes, guys. This is just drawing particles to try and think of the shape. Right. Oh, sorry, I did number 2 first. My bad. Okay. Yeah, I'm sorry. I was supposed to do carbon dioxide, but carbon dioxide works in the same way. What happens is the 2 goes here, and the 1 oxygen goes on this side, and these 2 from the carbon goes on this side, and the other one goes there with our X's there. Okay, so there you can see drawing from that electron to that electron, which means we've got 2 bonds or a double bond between C and O, and 2 bonds or a double bond between the other CO. Okay, so these are double bonds. This is a triple bond, and this is a single bond, and I've realized my mistake here too. I'm just getting lots of X. Sorry, I know. You know what? I'm the same no matter where I am, so I'm actually okay with it. Okay, sorry, it's Cooper notation, so we're only doing lines. Okay, then oxygen will have, again, we know that oxygen has 6 electrons around in its outer energy level, and so it will have 6 dots in the Cooper notation, and 4 of those become 2 electron lone pairs on either side, and then there's a bond with each. Oh, I've drawn them so far away again. So we are going to do that. Okay, so I'm going to just color in this one's electrons over there. Okay, and those are the electrons for this oxygen and that oxygen, and what we land up with, oh, what did I not do here? I didn't do one. lone pairs. Please remember your lone pairs. Oh gosh, there's a lot of planning, girls. I'm very tired. Okay, and we've got our lone pairs here, and we've got our lone pairs here. All right, and so there's our Cooper notation with double bonds or triple bonds. Now there's a new bond that I'm going to just talk about, and that is a dative bond. Okay, there's the word there, dative. Now this is something interesting, because if you think about ammonia, this is what our ammonia looks like. And we know that when you have ammonium, there is another hydrogen. So here is ammonium, and it's positively charged. Now what happens is, and this is where the question about those sigma notations came from, and we're going to do it a little bit later as well, is that this side, because there are only these lone pairs of electrons, and over here we've got quite positively charged hydrogens on this side, because their one and only electron is being pulled closer to nitrogen. So this makes this side slightly negative and this side slightly positive, creating this polarity. And then we get a hydrogen ion that is very commonly found in water, and it then attaches itself to that negative side of the ammonia, and it's actually attracted by an electrostatic force, because this is positive, and it's attracted to the negative side of that molecule. And then that's when we make the polyatomic ion of ammonium. And all the other ones are very similar to this as well. So that is what's called a dative bond, and it is represented by this arrow pointing to a lone pair. Now, what makes this different? Well, if we had a look here between, if I did this for the hydrogens, okay, you'll see that each one of these bonded pairs, okay, have one electron from each one. So here this one is from hydrogen, this one's from hydrogen, this one's from hydrogen, this one's from nitrogen, nitrogen, nitrogen. This bonding pair, so the electrons that are responsible for the dative bond, both come from the same atom. They both come from nitrogen. Okay, and that is what the major difference is here. That's page 3. Okay, so page 3 is what I asked you to do, so you should have it already. If you want to reprint it, please go ahead and you can write it. So I'm just quickly going to go through this briefly, because you did have a very good lesson with Tyler. So remember, the name of the shape is linear. Now, the way you're going to have to learn this is that if I give you any example, you need to then draw the molecule using Cooper notation or Lewis structures. Lewis structures would probably be better, but you can do it both or either. And based on your Lewis structure or Cooper notation, you can then decide what name it is. And then if you can decide the central atom, like I said, the central atom is usually the one with the lowest electronegativity. If you've got two atoms that are attached to that central atom, then, and you don't have any lone pairs, then it's linear. Okay, the trigonal planar, when you get back to school, I'll show you, we'll make these molecules so that you can see them in real life, the shapes. And what this is that it's a planar, so in other words, it's flat, it's all in one plane. And like that example that we did there. Carbon dioxide over here is also an example of this, so that's why I just put carbon dioxide there. The tetrahedral is the one that has 4 electrons around, also known lone pairs. Please note that I've deliberately separated the ones with lone pairs and the ones with lone pairs and without lone pairs. Okay, so these are not very commonly asked, but I would learn them. And again, when we look at them, I want to show you, when you come back, sorry, I want to show you what the shapes look like, and you can visualize it a lot better. Okay, so water is bent because of those lone pairs. Remember, those lone pairs are pushing down on those bonded pairs even more than a normal over here, even more than normal 4 bonded pairs. This one has 2 bonded pairs and 2 lone pairs, and these force the hydrogens away even more, and that bends the molecule. Trigonal pyramidal also comes in a 3-dimensional shape here, and it makes like a pyramid. If you had to actually connect these lines over here, okay, it's not very good, but you should be able to see like a triangular pyramid at the bottom there, and then your lone pair pushing them all down. Okay, so that is that. You hopefully have done this task, Think Tank 9.1. I only wanted you to do number 13 because it was quite intensive, quite a lot, and you had to do the first 3 columns. So now what we're going to do is looking at the polar and non-polar. So now this is starting fresh. So what I've done is that I've included a periodic table here with the electronegativities because it's very important now. So electronegativity, remember, is the tendency of an atom to attract a shared electron pair during bonding. So a shared electron pair is one electron comes from one atom, the other electron comes from the other atom, and they're sharing, but one of the atoms pulls more to the other if it has a higher electronegativity. So now there's 2 different types of polarity here. We are looking at a bond polarity. Please take note. It is a bond polarity and a molecular polarity. They are different. So when we are looking at the bond polarity, just like where I showed you to work out if it's an ionic or polar covalent bond, and you subtract your electronegativities, you'll get an answer. And so you have a polar bond. And we represent it this way. So how does this work? So if we take a look at hydrogen, it's got a 2.1 electronegativity. Chlorine has a 3.0 electronegativity. That means that chlorine pulls the shared electrons that they share closer to it. And what this does is that it turns this side more positive. Now you can have a look here. This makes a little plus sign over here. So it's telling you this is positive. And we do also, it's like an S that the tail links back up to it. And we can say positive. And this side is slightly negative. And that is how we show the bonds are polar. The bonds are polar. Okay, over here, if you take a look, our oxygen is 3,5, our carbon is 2,5, and then we have another oxygen at 3,5. You can immediately see here that we know we've got bonding pairs between the oxygen here and the oxygen here and the carbon, but what's happening is one is pulling, this oxygen is pulling these bonding pairs over here, this oxygen is pulling those bonding pairs over there. But I want you to imagine this as if they were vectors. Okay, so if one is pulling that way, one is pulling that way, and they are of equal strength, what is going to happen? They're going to cancel. Well, it's almost like cancelling out, like you do with vectors. And so this lands up not being different poles, because if you look here, your positive is in the middle, and you land up there. So you can't say this is positive and that's negative and that's negative. In order to have a polar, we have polar bonds, sorry, 2 polar bonds, but we don't have a polar molecule. So you can see that the polar bond is being pulled there. So this is called a polar bond. Over here between hydrogen, we've got 2.1 and 2.1. Okay, this hydrogen is pulling equally and to this hydrogen on the pairs. Neither of them are pulling more than the other. So this is then a non-polar bond. Okay, this is a polar bond and this is a polar bond. Basically, if you have to do that where they land up being together, it's non-polar. But we can see that if we subtract the 2, you'll get 0. And so it's a non-polar bond, and specifically a non-polar covalent bond. Okay, so just like you did that, you can figure that out by there. So these are polar bonds, non-polar bond. Now let's take a look. How does this work with polar molecules? Because this is important now. You need to be able to decide if a molecule is polar or non-polar. This will help you with intermolecular forces. So here we have this. We have HCl. We know that Cl has a higher electronegativity than H, so Cl will pull the bonding pairs that way. Okay, so that makes this one slightly positive side and have a slightly negative side. This is a polar molecule. Okay, this one here, remember we had in the middle it became positive, on the ends it became negative. But now look there, they're not on each side of the molecule, they're not different. So we can't say that this is polar because they are not different. And think of vectors here, I've even put the note here. This pull here will cancel with that pull here, leaving you with no pull. There is a zero resultant if you think of it as vectors. And so this will be considered a non-polar. Think about the poles of the earth. We know that we have a north and a south, so they are different. If we had a north and a north, we wouldn't have two different poles. They would be the same, and so it would be non-polar. But we know that we have polar earth. Okay, let's take a look very quickly at this. So I'm going to show you the bond polarity and hence determine the molecular polarity. So we are trying to find if your bonds are polar so that we can determine if your molecule is polar, so that you can determine your intermolecular force. So let's take a look. We know that this is being pulled like that because this is what we know already. Okay, let's take a look at our electronegativity here. So B is 2 and F is 4. Oh, what am I doing? Okay, is 4. Okay, so what do you think? 4 is bigger than 2, which means your fluorine is going to pull the bonding pairs of electrons more. So they're going to go in that direction, making this side positive. In that direction, making that side positive. In that direction, making that side positive. And so let's take a look. Now again, I want you to think of if this was on a Cartesian plane. Okay, remember your Cartesian plane in vectors. And you had a pull there and a pull there and a pull there. In which direction would your resultant be? So imagine that. Okay, and would you have a difference? So if we see that and we go, okay, well, mostly this is pulling down and mostly that's pulling up. But we are looking at the best way to find out if this is okay, if this is polar, is to see whether your molecule is also symmetrical. What does that mean? It means that if I was to draw a line straight down, can I fold it on there? Okay. If I draw a line there, can I fold it? If I draw a line there, can I fold it? This is a non-polar molecule. Okay. These basically cancel out. I don't think I've drawn the angles properly, but if you look at the angles, they will cancel out. And this will then be non-polar. Okay. Right. So in other words, you can imagine it being pulled in by equally strong forces in these directions, and these angles should be the same. And so this B, imagine this person standing in the middle there being pulled in 3 ways, equally spaced, same force, they're not going to go anywhere. Okay, so this is why it's non-polar. Let's take a look at ammonia. Sorry girls, I'm really tired. I only went to bed at 2 o'clock this morning. And there we have that. Okay, so this is our Lewis structure. And again, I thought I'd do the Lewis structure now because I want to show you then how you can make the Cooper notation again with this. So we're looking at the electronegativity over here. So we've got 2.1 for hydrogen and you've got 3 for nitrogen. And so that means nitrogen is going to pull stronger force on the bonding pairs. Okay, but I think you could already see that this one is polar because of that lone pair of electrons. That immediately makes this, that this side is slightly negative and this side is slightly positive. Okay, but if you have a look, and those two could cancel out, this one won't. Okay, so you can already see that this side's going to be positive and that's going to be negative. Okay, so this is polar. Again, let's take a look at the symmetrical or symmetry. Is it symmetrical? If I do that, I fold it on. Yes, I can fold it. But if I did this, can you see how I have a hydrogen here and I've got a lone pair there? I won't be able to fold it in half. It is not symmetrical, so it is polar. Okay, here, let's take a look. I'll go back to Cooper notation. Just showing you that you can interuse your Lewis and your Cooper. It's really no big deal. Okay, so there we have our carbon and our hydrogen for methane. And if you have a look, it's 2.1 and 2.5. So hydrogen's at 2.1 and carbon's at 2.5. So carbon is pulling them in. Okay, what do you see that's happening here? These two can cancel. They're directly opposite and they're of equal strength. These two are cancelling out. They are directly opposite and equal strength. So this is a symmetrical molecule as well. This can be folded on top of each other in many, many ways. Okay, and so we say this is non-polar. There's no distinct different side to the other. Okay, and that is that. All right, so girls, I want you to finish the last column of Think Tank 9.1, number 13, and please do exercise 9.1, page 130. It's not the whole exercise, it's just number 3 for me, please. I want to see if you can get this. On Monday, I'm going to give you a little task to do for me so that I can see how this is going. So it's going to be 4 marks. So on Monday, you're going to have your first task with me. We've got our triple. So I think I'm going to give you the first half an hour to do that. And then the next hour, I'll give you another video where I'm going to then use dots and all kinds of things to try and help you to understand intermolecular forces. Okay, I hope this has helped. Please, please, please keep asking me questions. If you don't ask me questions, I don't know if you're battling. I'm here for you. I hope you are well. These very weird times we're living in. I miss you guys crazy, especially Tristan's funny faces and Bali's shouting across the class. But I'm trusting you guys are well and keep safe. And talk to me, please. Let me know how it's going. If you're feeling scared about this work or if I really lost you, maybe try and watch it again, see what happens. Yeah, take care.